All right, here we are. Let's go ahead and jump right into it. We're talking about explore number 3 from Fundamental Forces. And the essential question that we have here in green: how were the 4 fundamental forces discovered? You can see that here on the right. So go ahead and take a moment and tell me what you know. You can hit pause on the video for a second, or what you think. Okay. All right. So we're back now. You've taken a moment to write down what you know or what you think. If we take a look at this explore, you can see the first thing they're going to talk about is gravitational force. Then they're going to talk about electromagnetic force. Then they're going to get into your nuclear forces, your strong and your weak nuclear forces. That's your 4 fundamental forces in total there. And then they go and finish up with just a little paragraph talking about the standard model, right, which incorporates 3 of those 4 forces. Okay. So we've broken our notes down the same way. On the right-hand side here, you can see gravitational force, Roman numeral 1. Okay. And I'm going to go ahead and expand on these notes, but you already know how this works. These notes are coming directly from your text, okay? And you have this kind of filmed here, so you can see my highlights. And I encourage you, of course, to read first and try to make your own highlights and then see if they match up with mine, okay? That might be a good idea. And don't forget to watch these videos and do any additional readings. Okay, so I'm going to expand here, and let's go ahead and make this a little bit larger so you guys can see these notes a little bit better. Okay. Roman numeral 1, gravitational force. It was the first fundamental force to be well understood. Okay, we can thank Sir Isaac Newton for that. He gave us the law of universal gravitation that describes the force. You remember the formula, F equals, and we could even write that out if we wanted to. Let me go here. We could say over off to the side, F, the force of gravity, was equal to the gravitational constant times the mass of object 1 times the mass of object 2 divided by the distance squared, right? Hopefully that's something that you're like, oh, I remember that. So what are the properties of gravity? Well, they can operate at long distances, right? The moon is not necessarily that close to us. It's pretty far away. And the sun is very far away. And yet we feel the effect of the sun. So it is a long range force. It is an attractive force. And I'm not talking about a good looking force here. I'm talking about attraction, like 2 objects being drawn towards each other. Maybe I am talking about things that look good. I'm just kidding. All right, even at huge distances, objects feel the attractive force of each other. Could you imagine if you were on one end of the universe and you had a planet, and then you went all the way to the other end of the universe? We're talking massive distances. Would those 2 objects be able to affect each other gravitationally? The answer is yes, even though it would be very, very weak. They work at infinite distances. It's kind of something that's difficult to wrap our heads around. So even at huge distances, objects feel the attractive force of each other. Okay, gravity keeps the celestial bodies in their orbits. That's why we're orbiting the sun. That's why the moon is orbiting the Earth. If there was not the gravitational attraction, we'd probably be zooming off into space in a straight line in a particular direction. But we tend to get tangled up with other objects through gravity. And that's why we see all these different things orbiting each other in space. Okay. Um, You might think of an orbit as being circular. Most of the world thought it was until a guy by the name of Kepler came in and said that the orbits for most of the planets are a little bit more oval shaped, or what we call elliptical. Okay. Um, Towards the end of these notes, you'll see that the three of the four fundamental forces fit into the standard model. Gravity does not fit into the standard model. They're working on that right now. Gravity is described using Einstein's theory of general relativity. Okay. Okay. So moving on to the second fundamental force of the universe, electromagnetic force. Um, if you noticed that electro and magnetic seem to be two different ideas blended together, you're not crazy. We used to think that they were separate forces, but today we link them through the theory of electromagnetism, and that's why you see it titled as electromagnetic force. It does occur between charged particles, right? One object has a positive charge, one object has another positive charge. They're going to repel each other, like charges repel. Negative would repel negative. On the flip side, if you had two charges, one positive and one negative, they would be attractive forces. They would not be repulsive forces. Okay. And there was a fellow who was able to describe this with a formula. Coulomb was his name, French man. Um, Coulomb's law was an early statement describing this force, and this came in 1795. And the formula is very similar to the gravitational formula. It says something to the effect of the electrical force is equal to I should put Coulomb's constant times the charge of object 1 times the charge of object 2 divided by the distance squared. And hopefully you look at that and you say, boy, that looks very similar to um, Newton's uh, gravitational formula. Very similar, right? Letter C. In 1831, Michael Faraday showed that electric currents can create a magnetic field, right? The cord that connects the wall to your computer when you're charging your laptop. Um, as electricity runs through that wire, it produces a magnetic field around the wire. Okay. And a moving magnetic field can induce an electric current. So if you take an electric field and move it around, you can actually generate electricity. That's pretty interesting stuff. As a result of Faraday's work, if you look over here on our side margin, we have motors today, and we have generators, electrical generators. Those are working simply on Faraday's two ideas. Okay. Michael Faraday's ideas allow the transformation um, of electrical energy into magnetic and magnetic into electrical, back and forth, back and forth. Letter D, 1864, James Maxwell realized that the connections between electricity, magnetism, and light, he realized that there was a connection between these three things, and he published four equations in 1873 that related them together, and we use those formulas today to make predictions and describe relationships. Okay. Notice on letter E here, electromagnetism today is explained using the Standard Model, which also includes the strong and weak nuclear forces. Okay, so there's four fundamental forces. Gravity is lumped with the theory of relativity until we get a unified theory to connect it to the Standard Model. It'll be described with the theory of relativity. And then electromagnetism, strong and weak nuclear forces will be described with the Standard Model. All right, nuclear forces, Roman numeral 3. There's two types. You have your strong and you have your weak. Have you ever wondered to yourself if you have an atom and the inside of the atom has only protons and neutrons? Neutrons are neutral, they don't have a charge. Protons are positive. So, how do you squeeze all those protons inside the nucleus and not have them repel each other and break apart? The answer is gluons, Gluons here, letter A. You can see that. These are massless particles that bind quarks together. It gets just stranger as you dig deeper into the world of physics, right? So we have this term to describe a massless particle that seems to be holding these things together. Weak nuclear forces. What about these guys? This is an interaction between your subatomic particles that is responsible for radioactivity. You watch these Marvel superhero movies and you see how Spider Man is the result of somebody getting bit by a radioactive spider. It seems to be a theme with Marvel superheroes. There's always radioactivity going on, or a lot of times. Well, radioactivity is a result of these weak nuclear forces, okay, allowing for protons to morph or change into neutrons, and vice versa. Neutrons can morph and change into protons. When they do this, they're going to emit radioactive decay. Okay, so radioactive decay is related to your weak nuclear forces. And that brings us to Roman number 4, the Standard Model. It describes strong and weak nuclear forces, as well as electromagnetic force. This model was developed after the discovery of quantum mechanics in the 20th century, right? As you had people like Einstein who were contributing to this. You had people like Oppenheimer from the movie developing the atomic bomb. We started to develop particle accelerators and starting to smash atoms together at the speed of light. We've been able to observe these smaller particles that seem to hold the atom together. And that's where we, in developing our quantum mechanics, we also developed a standard model. Both of these models describe the subatomic world. All right. And I think that's pretty much it. So I hope that you got all of that. I'm just going to draw this, and I'm going to draw this. And you know what's coming up now? Go ahead and write me a summary paragraph. Okay. Give me a good 2 or 3 sentences in your own words. Tell me what you just read, what you just wrote, what you just heard. Okay. Try not to look at your notes. Try to do it from memory. And try to be as thorough as you can, right? We're in the business of getting this stuff to stick. All righty. We'll talk to you guys later.